Hello everyone, my name is Natchamon. I'm Master Course student in School of Chemistry at Suranali University of Technology, Thailand. I would like to talk about the synchrotron SAXS and DSC to study of the metabolization kinetics of short branch and linear isotactic polypropylene. Isotactic polypropylene or IPP is a typical semi-crystalline polymer that has become one of the most widely used in industrial and commercial applications. It has many desirable and beneficial physical properties such as the low density, high melting point, and chemical resistance. However, the commercial polypropylene usually have relatively low well strength and no stain handling behavior. So, these limit their use in the applications such as the thermoforming and blow molding. To improve some property of PP, the one built-in defect will add two PP homopolymer to random copolymer. For the synthesis, you can use the high-activity synchrotron catalysis. But in this project, we didn't synthesis, but we obtained our sample from the Sinopec company. We have three samples. The first code name is V30G. This is the linear IPP. And MT series, we have two samples. This number represents to the melt flow index following this table. We expect that the MT12 has higher percent built-in defect than MT18, but now we cannot measure them. So, from this work, we want to investigate the effect of short-chain bond on crystallization characteristics and phase morphology of isotactic polypropylene using the thermal analysis and X-ray spectrometry. The first method, we use the DSC study in a non-isothermal crystallization. We start with to heat sample from 50 degrees Celsius to 200 degrees Celsius and hold for 5 minutes to erase the previous thermal history. Then we cool down sample to 50 degrees Celsius and vary 6 different cooling rates between 5 to 30 degrees Celsius per minute and obtain the raw data of the DSC result. Then we will determine the onset and peak crystallization temperature. The onset crystallization temperature is mean the point that the crystallization can start, and the peak crystallization temperature is mean the point that completely crystallization. Then we will show the parameter in the table 1. From table 1, you can see that both on the onset and peak crystallization temperatures shift to lower temperature with increasing the cooling rate. This indicating that the lower the cooling rate is, the easier is the crystallization will occur. And we will process data from the raw data to this figure to determine the relative crystallinity with temperature and time. Using this integration, this equation used for integrate the peak area. From the half-time of non-isothermal crystallization, it decreases with the increasing the cooling rate. So, adding short branch defect creates lower crystallization. Next, we will use the other model to employ analysis. The first model we use a Abrami model. In general, this model used in the isothermal crystallization, but in this case, we try to use in the non-isothermal crystallization. This equation is the Abrami equation. Xt is relative degree crystallization at time t. N is the Abrami constant, which represents the dimension of gold crystal, and C is the non-isothermal crystallization rate constant. And when we can determine C, we can use this equation to obtain this parameter. From the Abrami result, we can calculate the kinetic parameter shown in table 2. From this table, you can see that the crystallization rate constant or C is increased with faster cooling rate, and the exponent or n shows that in the scatter data in the broad range. N for VT0G is larger than the other sample at the same cooling rate, and the crystal dimension for V30G or linear IPP is equal to 3 dimensions, where the short band defect exhibits more likely toward 2 dimensions. The next model we use Osawa model. This model modified from the Abrami model. This model used in the isothermal crystallization to the non-isothermal crystallization by assuming that the crystallization occurs at a constant cooling rate. But we not use this equation because we don't have the linear part from this equation. So we will skip to the other equation. These are called the mole equation. From this equation, they combine with the Abrami and Osawa together. And this is equation of the mole equation. N and M are the Abrami and Osawa exponents, and Ft is cooling rate chosen to attain a certain degree of heterogeneity at a unit crystallization time. And we can calculate the parameter shown in this table. The Ft increased with the increase of relative crystallinity. This means that the larger the relative crystallinity required to attain at a unit time, the faster the required cooling rate will be. When compare trend of Ft, it can be found that the trend of Ft value of PP with defects are larger than linear IPP, and the overall crystallization rate of short band is slower than linear IPP. The next method we use SAXS and Vao. SAXS is small angle scattering technique used for determination of the microscale or nanoscale structure of particle system, and Vao is similar to SAXS, but the distance from the sample to detector is shorter than, so the diffraction maximum at the larger angle are observed. From this slide, we will show the data processing. This is the raw data of SAXS, and we will use the SAXS program to make the SAXS profile. And Q is the scattering vector, and theta is the scattering angle. For the isothermal crystallization behavior of our sample was determined by the beamline 1.3 W of the Siam Photon Laboratory Synchrotron Light Research Institute, Nakhon Ratchasima, Thailand. This slide shows the Lorentz collected SAXS profile at different crystallization times. You can see the evolution of the first scattering peak of V30G is slower than other sample. This means that this sample has longer induction time compared with other sample, and the scattering peak of VT0G is significantly higher than other sample, implying the larger amount of crystallinity. Then we use the electron density correlation function to estimate the average thickness of the amorphous and crystalline region. We use the inverse Fourier transform to convert the Q space to C space and obtain this curve. In the sum point of this curve, we can calculate the lamellar parameter. We focus on 3 parameters. LP is the long period covered with crystal and amorphous region, and LC is the crystal phase, and LA is amorphous phase. The parameters shown in this slide, long period of VT0G is about 18 nanometer, and the long period of MT12 and MT18 is about 24 nanometer. And the short run PP has thicker amorphous phase region than linear IPP, where the crystalline thickness are about the same. And the short run defect cannot incorporate into the crystal structure of isotactic polypropylene, but should be accrued to the amorphous region. This slide shows the wax analysis. This figure shows the wax diffractogram. You can see the diffraction peak at around 17 degrees appear for the MT series. For the wax profile indicating that the unit cell of polymer may be changed. And from this curve, we can calculate the degree of crystallinity using this equation. Sum of DSC is the summation of the peak area of the crystalline phase, and AA is the peak area of amorphous peak. Then we will compare the percent of crystallinity both of wax and DSC technique. You can see the percent of crystallinity of V30G is the most when compared with MT series. This means that the one built-in defect hinders the crystallization process of IPP. So, for the summary of this work, the one built-in defect hinders the crystallization process of IPP, and the crystal dimension of linear IPP is close to 3 dimensions. In case of the short band defect, exhibit more likely toward 2 dimensions. And the short band defect with PP homopolymer has thicker amorphous region than linear IPP, where the crystalline thickness are about the same. We would like to thank the IRPC, Chinopec Company, Kyoto Institute of Technology, and Osaka University for support us. Thank you for your attention.